Okay, so last time we already discussed about the shear force. Okay, the critical reserved shear force. That is the stress required for sleep to occur, right? And therefore, we can realize that the number of sleep systems is correlated with the sleeping process of the metals, right? Therefore, the higher number of sleep systems have the more sleep plan and directions. That's mean they have the high ductility, right? Correlated with the high ductility. Okay, therefore, we can look at the different crystal structure with different sleep system. For example, for HCP structure, okay, which has the for HCP structure, which has the few sleep system, only 3 sleep system. Therefore, its ductility is pretty low. Okay, and for the FCC structure, has 12 sleep system. Okay, hence they have the high ductility. And for BCC structure, okay, they can have up to 48 sleep systems. Okay, it's very ductile. Okay, it's very ductile. In the cross sleep occurs when a dislocation moving along the sleep systems or starts moving in a different sleep system when it encounters an obstacle, that's a barrier. Okay, that's why I mentioned before, when this sleeping process occur, the dislocation moves, right? The dislocation move, and when the dislocation encounter a barrier, they cannot keep moving. They cannot keep moving. You stop, and it will now will move in a different sleep system. It kind of change its orientation or direction for sleeping. Okay, for sleeping. Okay, so let's look at the closed system, which composed of sleep plan and sleep direction, right? And the sleep plan is the highest planar density, right? So that means it's the close pack plan, right? Close pack plan. Okay, and the sleep directions are with the highest linear density. That means the close pack direction, right? Direction. Okay, therefore for FCC structure, whose close pack plan is 111, right? It's 111. Okay, and its close pack direction or the sleep direction is 110. 110 family. 110 family. Okay. If we can look at the top view of the 111 plan, this is the 111 plan, and it has the 110 sleep direction. Okay. Therefore, the BCC's crystal has 48, have up to 48 sleep systems. Okay, and with the high B over A ratio, therefore they have the good strength and the moderate ductility. For FCC crystal has 12 sleep systems. Okay, with low B over A ratio, they have the moderate strength and good ductility. And for the HCP structure has only 3 sleep systems. Okay, therefore the most of the HCP structure brittle at room temperature. Okay, at room temperature. Okay, so how to define the? We already defined the sleep plan and this direction. And what is B over A ratio? We mentioned here the B over A ratio. What's the definition of the B over A ratio? As B over A ratio decreases, the shear stress required to cause slip decrease. That means we just need a lower shear stress to make slip occur. Okay, so we can see this is the B, this is the A, and this is the slip plan. This is the slip plan, right? This is the slip plan. Okay. Okay, we can say the B is is called the interplanar distance between the closed back plan. Okay, closed back plan, and A is the lattice parameter. Okay, so as the ratio of B over A decreases, the shear stress required to cause a slip decreases. Okay. And this is a compare. This figure shows the compare between slip process and the twin. As I already mentioned previously, that the slip occurs along a slip plan, right? A slip plan. And when the twin occur along the twinning plan is like a mirror, right? It's like a mirror. As the shear stress occur on the crystal structure, in the crystal structure, we are mirror along the twinning plan. It's the symmetric. This is symmetric. Okay, so it's original structure when the shear stress applied on it, and it has the twinning plan. It's a twinning plan, and the crystal structure is a mirror along this twinning plan. Okay, it's along the twinning plan. Okay, so you can imagine that why we saw the lower B over A ratio right here. That's mean the interplanar distance, because the lattice parameter is a constant, right? And the interplanar distance, or we say the despacing of the closed back plan, it decreases. That's mean the shear stress required decreases, right? To make the slip process occur. Why? Why? If A is a constant, why the short distance between the interplanar distance can reduce the shear stress? So you can think of this way, as this B parameter decreases, that's mean what? We have the we can say we have high stiffness. We have a high stiffness between the atoms, right? We have the high stiffness. Do you still remember we have this plot, right? This point is R naught, right? And it's the repulsion, and it's attraction, right? It's attraction. Right. Therefore, if the interplanar distance is shorter, at least I can reach the equivalent distance between two atoms or particles. That's mean the high stiffness, the slope of this the F versus distance figure. The slope of the F over R is higher. Okay, therefore the high stiffness provide the I mean, they are not easy to break, right? The atom is not easy to break. Okay, Therefore, the bonding force between this direction, this bonding is stronger than this. Okay, than this. Therefore, this plane, when we apply a shear, this bonds are not easy to be broken. Okay, therefore, this direction is stronger than this direction. Okay, so that's the reason why the crystal plane or the crystal structure will slide along this close-packed plane. Okay, it's not, this direction is not easy to be broken, and this direction is easy to slip. Okay, it's easy to slip. Okay. So this figure shows the slip system with different structure, metal structure. Okay, as I already mentioned, for example, like the FCC structure, we have the highest, the close pack plane, right, and we have the close pack direction right here. Okay, so you can try to plot this slip system with different crystal structure. Okay, I just give you an example. For example, like the FCC, whose slip plane is 111 family, and its slip directions are 110. Okay, so let's look at the surface defect, which includes the boundary, the grand boundary, and the plane. Therefore, the surface defects are boundaries or planes which separate materials into regions, which might have the same crystal structure but different orientation. Okay, and the materials in interior surface represents the surface where the crystal structure abruptly ends, and the surface atoms have incomplete bonding, and the surface might rough and very reactive. That means the boundary, the grand boundaries are very reactive. Okay, are very reactive. Okay, so let's look at the let's show you a figure first. Okay, for example, we have the, for example, this is the SEM scanning electron microscope of the metal with different grain size and grain boundary. For example, this is the grain size. This is the grain size. This is the grain. This is the grain. This is the grain. And this is the grain. Okay. This is the grain. And the grain size is highly influences on the materials, the metal's yielding stress at room temperature. Also, the grain size, the effect of the grain size is highly influences on the this surface property of the metal or steel. Okay, so you can imagine that if the grain size is not uniform, if we have a painting, we have a color pen, we have a die down a metal sheet, so the uniformity of this painting must not be uniform, right? If the grain size is not identical, mostly identical. Okay. Okay, so let me ask you guys a questions. This is the grain boundary. Okay, this is the grain boundary, and we have a different orientation. For example, this surface maybe is 111, and this surface maybe 110, and this surface maybe 100. Okay, if we have a higher density of grain boundary, for example, we have this is a grain boundary, is a grain boundary. Okay, so it's like this. So the higher density or the higher number of grain boundary gives the higher strength, gives the higher mechanical strength or not. I mean, well, the higher number of grain boundary gives the higher mechanical strength or not. So the answer is right here. When we increase the material strength by reducing grain size or increase the grain boundary, we can increase the material strength by reducing grain size or increase grain size. Why? Why? This is the reason why. The dislocations can only travel a short distance. So what's that mean? What's that mean? I just erase some grain size. Okay. For example, this is our grain boundary, right? Sure, this is our grain boundary, right? When these materials, when the shear stress applied to these materials, the dislocation occurs, right? For example, we have a dislocation here, edge dislocation, we have the edge dislocation, we have edge dislocation, okay? So when the dislocation keep moving, when it encounters grain boundary, it will be stuck. So the grain boundaries can be regarded as a barrier or the obstacle for dislocation movement. Okay, so for example, when this dislocation move, oh, he encounter a barrier, and this grain boundary move, oh, yeah, there's no barrier. Okay, therefore they can keep moving. Okay. Okay. In other words, if we have a higher number of, if we increase the number of grain boundary, for example, if we have our grain boundary, such like this, grain boundary. Okay, so why the higher density of grain boundary has the effect on enhance its mechanical property or strength? Why? Why? Because the distance of dislocation movement is short, right? So if we have the higher number of grain boundary, what's going to happen? For example, this dislocation, when it move, you will be stopped, right? When you move in this direction, oh, stop it, because it encounter a barrier, right? And when this dislocation keep moving, oop, he encounter a barrier, it stop moving. The same, the dislocation moving, oop, he hit the barrier and it stops. It stops to moving, right? Stop to move. Therefore, therefore that's why we say we can increase the material strength by increasing the grain boundaries. This way, the dislocations can only travel a short distance. Okay, can travel a short distance. Okay. Okay, so let's look at the equation called the Hurlpack equation, which is relates to the grain size to Ionic stress. Okay, I will discuss what the Ionic stress is. Okay, so when we have the a metal rod and we apply a tensile stress, especially for the metal, and we got a strain and the stress curve. So we have the stress and strain curve, okay, such like this. Okay, and we will get a stress called the yield stress. The yield stress means when we apply a stress below the yield stress, that's mean the elastic deformation occurs. Okay, when we apply a stress and which is higher than the yield stress, when we apply stress higher than yield stress, for example here, that's mean the plastic deformation occur. Okay, that's mean when we release the force or when we release the stress, the dimension change will not return to its original dimension. Okay, therefore this equation is coming from experiment. Okay, that means we fabricate alloy or metal, and we measure its grain size by microscope. We just observe its grain size via microscope, and we do the tensile test. We can have this stress and strain curve, and we figure out the yielding stress from this stress and strain curve corresponding to the grain size. Okay, and we work on the numerous experiment on this. We will get this linear equation, this whole patch equation right here. Okay, therefore it's from experiment. Okay, and the D here is the average diameter of the grain. We can measure it from the microscope, and the sigma Y is the yield stress. We can measure it from the tensile test, and the sigma naught and the K are constants for different materials. Okay, from different materials. For engineer, we like to put all those unknowns into constants. Okay, therefore, from this experiment, we figure out this equation, this linear equation, and we can plot this in linear equation, right? Therefore, we can find the relation between yield stress and the grain size. Right? We can find the yield stress corresponding to the different grain size. Okay, therefore we can test the different process or different metals or different alloys. Okay. And there's the other way of specifying the grain size is the STM. The grain size number n, when we observe it under the 100 times of the optical microscope. Okay. So the n defined as the equals to 2 of the power m minus 1, and which represent the number of grains per inch square. Okay, that's mean, for example, we have the observe the grain size under optical microscope. We have the 1 inch square, the area, and we observe the number of grains in per unit area. Okay, per unit area. Okay, and we figure out the number of n, and we plot this n into here, and we can get this capital N. Okay, the capital N is the standard of STM to define the grain size, to define the number of grain size. The higher N means the higher number of grains per unit area. That's the inch square. Okay, and the small angle grain boundary is an array of dislocation that produces small misorientation between adjacent crystals. Okay, let's show you a 3D picture like this. So when we observe the grain size from a microscope, no matter the optical or the TEM, whatever, this grain size is 3D structure, right? You can see this grain size has a depth into the screen, the depth. Therefore, we can plot this each grain size in 3D, right? Like this, right? And there's a small, this is the 1 grain, this is the grain. And this is the other grain, And this is the grain boundary. Okay, this is the grain boundary, it's a surface. Okay, and the small angle grain boundary is right here. This is a small angle. Okay, and the grain might twist it. This grain might twist it. Okay, therefore this region is the grain boundary. Okay, it's the grain boundary. It is from the 3 three-dimensional perspective to look at the grain boundary. Okay. Therefore, from the TEM, this is the transmission electron microscope right here. We can look at the small angle grain boundary right here, right? It's a small angle right here. Okay, and we have one orientation right here and the other orientation here. Okay, it's called a surface defect. And as I mentioned previously, the twin boundary, that's mean a plane cross which there is a mirror image misorientation of the crystal structure. Therefore, when we apply a stress on the metal, and its crystal deformation might be slip process or twinning, okay, or twinning. For example, we have the crystal structure like this, and when we apply a shear stress on it, so the atoms move, right? Atoms move. If we can observe a twin plane is a plane like a mirror, right? Like a mirror. What's the characteristic of the mirror? The image is symmetric, right? It's a symmetric. If this atomic structure deform, and if there's a mirror plane, and we saw this deformation or this process as the twinning. Okay, it's twinning. Okay, so we can look at the structure is mirror image. It's a symmetric, right? It's a symmetric. It's a symmetric. It's a symmetric. This is the mirror. This is a mirror, and it's a symmetric. This is symmetric. Okay, symmetric. Okay, so we can look at the different mechanism of the slip or the twinning, the slipping process or twinning. Okay, slip process or twinning. So for the slip, we have a slip plane right here, the closed pack plane, right? For the twinning, we have the twinning plane. It's a mirror. Okay, it's a mirror. Okay. Okay, so the same example when we have the structure. Okay, have a structure like this, and we apply the shear stress on it. So after deformation, after the atomics moves, right? So, for example, the atom from here to move to here, the atom from here to move to here, the atom from here to move to here, and some atoms move, like this. After deformation, if we can find a twin plane under a microscope, that means we find a plane and the atomic arrangements are symmetric along that plane. So we can find the symmetric atomic structure, this and this. Okay, and we can say, okay, it's a twinning process. Okay, it's a twinning process, but not a slip process. Okay, but not slip process. Okay, so we can observe some. I just show some academic paper. It shows I think it's a PD. Okay, so it's created from the FIB, focused ion beam. Okay, to just slice metal with a very thin slice. Okay, thin slice, and we can observe the structure is this is the mirror, right? It's a mirror plane. That's a twin plane, and we have a symmetric structure. We have a symmetric structure along this mirror plane. Okay, along this mirror plane. Okay, therefore we can say, oh, this structure is a twin. It's a twin plane here. Okay, it's a twin plane. Okay, so if you guys want to realize more about FIB, you can discuss this later, or you can leave a message for me, I just want to this figure just want to shows you. Okay, we can observe clearly the twinning plan and the structures are symmetric along that twin plane. Okay. Okay, some importance of defects. Okay, so as we already mentioned previously, that the defects play an important role in controlling the mechanical property of materials. Okay, usually metals by interfering with slip and strengthening the metal. Okay, when the defect, you can think of what kind of defect you want to apply to this material to strengthen its mechanical property. Normal sawing, and the defect already mentioned previously. What the point defect, the line defect, and the surface defect, and all those the function of those defects is to strengthen the material's property or the mechanical property. Okay, so you can think of, okay, so what kind of defect we should apply to those materials? Point defect or dislocation or the grain boundary. Okay, so if you are engineer, a mechanical engineer, you have to think of what types of defects can enhance the highest mechanical strength with the lowest cost. Okay, and the defect has the less effect on ceramics. Well, because the ceramics has the higher hardness than that of metals. Okay, when the defect form in a ceramics, that's mean higher porosity in the ceramics. So when we calcinate it or when we pyrolysis the ceramics, there's some pores inside the ceramics. That's mean, well, the property, the characteristic of ceramics is brittle, right? It's brittle. If there are some pores inside the ceramics, what? It'll become more fragile, right? More fragile. Okay. And the strength hardening is to increase the dislocation, density. When the dislocation density increased, that's mean what? That's mean it cannot have other dislocations to move, because the dislocation will be stopped by dislocations. Okay, the same concept of the grain boundary, which is the barrier to stop dislocation moving, right? The same concept as strength hardening. Okay. Okay, so the effect of the strength hardening can be reversed. That means its mechanical property can be returned or released by heat treatment, or we can call it annealing. Okay, we can call it annealing. Okay, when the materials become harder during strength hardening, and we put this material into oven or furnace to anneal it, to heat treat it at a certain temperature for a long time, for certain time, and its crystals will recrystallize during aging. Okay, will recrystallize. Okay, and the solid solution strengthening takes place when the atom or ions as a gas materials are incorporated into a crystal. So I will discuss this in next few chapters, that we make some alloy. Okay, we add some other metals as the interstitial or substitutional atoms. Okay, to strength, to kind of point defect. It's kind of a point defect to strengthen the metals. Okay, and the third strengthening called the grain size, I already mentioned, right? The grain size strengthening occurs by increasing the number of grains or reducing the grain size, or we can increase the grain boundary, right? That can be regarded as the barrier or obstacles of dislocation. Okay. Okay, so we'll end up here. And next chapter, we're gonna discuss about the diffusion. The atoms or ions move inside the materials.